Hello? Kita screen itu kita ada di YouTube ni. Maka ada di Google platform yang cukup, ada di Google kita kita ada screen ada ni, black ada. Hello. Masih terlibat. Jangan dapat ya.
നമസ്കാരം മനോജ്. Asunle, hello.
സാറേ കേക്കാവേ.
അവർ 4 മിനിറ്റ് കൂടി കേട്ടു തുടങ്ങിയപ്പോ നമുക്ക്.
ഓക്കെ റൈറ്റ്.
Krishan, hello. Okay. Good morning, everyone. Welcome to the second lecture of the webinar series being organized by Cusat-Ncpor Center for Polar Sciences. We have Dr. Manoj, who is a research scientist at National Oceanographic and Atmospheric Administration's National Center for Environmental Information at University of Colorado, Boulder, USA. In fact, it is midnight for him. He is very keen and very enthusiastic to interact with the crowd. We had a very good interaction for the first lecture. Martin Lohnen delivered a lecture on the migratory goose, barnacle goose, various aspects. And I'm very sure Dr. Manoj's topic on wandering of the geomagnetic poles will be equally interesting because it's a very interesting title, and I'm very sure that will evoke a lot of response, a lot of interest among the researchers. And I really thank Manoj for accepting our invitation readily, and waking up at midnight to, it is in fact 11:30 midnight for him to give this lecture. I invite Dr. Sunil for formally introducing our speaker of the day, Dr. Manoj.
Okay, warm good morning to all of you. Am I audible? Hello? Yeah, okay. Yeah, indeed, it is a great privilege and honor to me to welcome one of my closest friend, I would say, rather than a eminent scientist in geomagnetic field, because I have almost a long association, in the sense it is almost more than 30 years of association with Dr. Manoj, being a good friend of mine, as well as one of the eminent researcher in this geoscience field. And because apart from all, he is an alumni of our School of Marine Sciences, as well as the Department of Marine Geology and Geophysics. He actually from the marine geophysics field, he was in the second batch, and he completed his MSc Tech in marine geophysics during 1992-97. Before going to, just I thought to, because I wanted to express that he is one of our alumni members. And before then, just I am entering to my duty to introduce Dr. Manoj, because in this under this Cusat-Ncpor Center for Polar Science, we will be having an audience from all the fields of marine sciences. Hence, I thought to introduce Manoj to the other audience as well. Dr. C. Manoj is a senior research scientist at the University of Colorado and a member of geomagnetism team at NOAA's National Center for Environmental Information, located in Boulder, Colorado, USA, which produces global geomagnetic field models such as World Magnetic Model and the High Definition Geomagnetic Model. He received an MSc in Geophysics from Cochin University of Science and Technology, India, followed by a PhD in 2004 at the National Geophysical Research Institute, NGRI, in Hyderabad. Manoj worked as a scientist at NGRI for years 1999 through 2007. After a postdoc in GFC Potsdam, Germany, he started working at NCEI as a research scientist in 2007. His primary interest lies in geomagnetism, with a focus on modeling and forecasting of the geomagnetic fields using data-based techniques. Manoj has authored and co-authored more than 60 peer-reviewed publications. Manoj funded NOAA Citizens Project that is named as CrowdMag to collect magnetic data from smartphones and to make the model global model. And still, because we were also part of to provide the data, because I remember myself, Krishnan and Hathasar all were in the Arctic regions. From there also we given some data to input as a model for to make the geomagnetic field model. In 2017, he co-funded Flatterns Geomagnetic Service LLC to provide specialized geomagnetic field services to the oil and gas industry. Apart from all, he has received so many awards from the US itself as a researcher in the area of geomagnetic field. I am not going much detail into that one. In these few words, once again, I wholeheartedly welcome Dr. Manoj one of my, as I told, my friend Manoj to deliver his talk to the audience from this marine science field. I hope that, because as I already mentioned to him, that because we were having a different audience from the different areas of marine sciences, hope he must have prepared the title also accordingly. Once again, I welcome Dr. Manoj to deliver his talk, and I hand over the mic to Dr. Manoj. Thank you, Manoj.
Thank you, Sunil. That was an awesome introduction, right? I almost never had such great introduction by anyone. Yeah, you mentioned this 30 years, and it's amazing that this goes all the way back. But yeah, I do want to start formally saying that I deeply appreciate the invitation from Professor Sunil and Professor Had for Cusat-Ncpor Center for Polar Science webinar series. And during the initial discussion, we were wondering what to talk about because I work on geomagnetism, and we selected geomagnetic pole. So it moves. So we used wandering of the geomagnetic pole. Yeah, I tried to make this talk general. One of the problems of making a talk general is that you never know whether you're straddling into some field which you're not very good at it. So I tried to make geomagnetic pole as a general talk, but yeah, I apologize if you find some rough edges in the talk. So I'll first talk about a little bit of who we are, what we do at our NOVA series geomagnetism group. I'll talk a little bit on the general geomagnetism history, which has some great connection to India. That's very, very cool. And I'll talk about on our overview of this geomagnetic field, where it comes from, and then some techniques how we make geomagnetic models. And then we go a deep dive into the core, where everything happens, this dynamo. And then we come back to the pole, where this dynamo causes the pole to change, pole to create aurora, and all kinds of other very beautiful things. And then I'll open it up for question and answers. So ours is a small group of scientists and technicians and software engineers working at University of Colorado, but our offices are in US National Oceanic and Atmospheric Administration, NCI, so we have kind of a dual affiliation. And we conduct fundamental and user-driven research in geomagnetism. It's mostly like, probably Geological Survey of India. Like we have certain user demands, and many of our research are focused towards those user needs. And we develop and distribute magnetic reference models. Some of you may understand, you may know already about, like International Geomagnetic Reference Field, IGRF. At least people from Indian Institute of Geomagnetism, if they are here, they will know. We do some real-time modeling. And we also have a large online repository of the magnetic survey data, possibly the largest in the world, with all the marine track line and aeromagnetic data, which is publicly available. And we also conduct this CrowdMag Citizen Science program. And I'm not going to detail on that, because that's not my topic, but you will find more details in our URLs below. So a short history of the geomagnetism. It has been known to humankind, a long time, that certain materials, if you suspend or pivot on a sharp edges, it kind of points towards the north or south. And one of the documented evidence for that comes from this Chinese compass, which is a naturally occurring kind of lodestone-based spoon, which when they put that on a brass table, the handle of the spoon turns to the south. It has never been used for navigation. It's Chinese equivalent of Indian Vastu. They kind of used that for certain ornamental purpose, but later on it was developed for marine navigation. But first kind of solid book on geomagnetism came in 1600 by William Gilbert, who was a physician to Queen Elizabeth I. He did several experiments, and he published this book in 1600, De Magnete, where he declared that, hey, Earth itself is a giant magnet. So that's why when you have a second magnet, it's pointing to the north. And that was a great discovery at that time. And another thing I want to point out is Halley's chart. Halley, you may know the Halley's comet. The same Edmund Halley did some cruise across Atlantic Ocean in 1700 and measured the declination. Declination is the angle between the geomagnetic north and the true north. So using a sextant with some tracking some celestial object, you can find the true north. With the compass, you can find the magnetic north, and the angle is what the declination is. So he plotted this angle around the ocean, and he published this chart for navigation purpose. And this thick line where I pointed is the zero declination. That means along that line, if the ship passes, the compass always points north. And that was another great contribution to geomagnetism at that time. Then coming to India, in 1840, the Geomagnetic Observatory started measuring a regular measurement of Earth magnetic field at Colaba near Mumbai. And the top picture shows the Colaba Observatory, which operated till 1906, when Bombay had the first electric streetcars. Started making noise to the measurement. Then they moved to Alibag, where it still operates. So combined Alibag and Colaba, we have one of the longest geomagnetic time series, possibly the longest geophysical time series ever measured in the world. So that's quite an accomplishment. In addition to that, on the right side, the Colaba Observatory in 1859 measured the geomagnetic storm, the largest geomagnetic storm ever happened, measured in human history, which is called Carrington storm, because Carrington in London found that after seeing the sunspot, after a few days, he started seeing compass vibrating. So he first made that connection, that sunspot and geomagnetic storm. So that big storm happened, and Colaba is one of the few observatories in the world we have such measurement, where we have seen this large spike in the horizontal intensity measured at those, which is still used for studying the geomagnetic storm. Personally, for me, so when I first went to NGRI as a PhD student, I was sent to NGRI Observatory in Itiyapuram. So what is plotted here is there are two plots, and these lines are called inclinations. These are, you can consider when the inclination is zero, the geomagnetic field is horizontal. It's just north-south. There's no vertical component. So it's the green line can be considered geomagnetic dip equator. And for space physics, this is an important phenomena or important feature, because the large equatorial intensification of the ionospheric current happens here. So NGRI installed an observatory under this green line in Itiyapuram in Tamil Nadu in 1960s. And when I joined my PhD in 2000, I had to take this magnetotelluric equipment and then do some calibration at the Itiyapuram Observatory. But by the time, if you see on the right, you can see that the dip equator passed down. So it's no longer above the observatory. And soon that observatory found itself useless, and NGRI closed that observatory. So, geomagnetic changes also has several other implications. So 3 parts of geomagnetic field. I just want to roughly touch where this may, if you put a magnetometer, which is the way of measuring the magnetic field anywhere in the world, about 95% of the strength you observe on the surface comes from Earth core, which I'll talk about later. And one of our model, world magnetic model, captures that. The way we model that model is using satellite data. Low Earth satellite or data has this high quality magnetic measurements. But if you remove this 95%, there are 5%, but they are still important. One important part is for crustal magnetic field. So the upper 30 or 40 kilometers of Earth's surface from down has this rocks which has magnetic content in it, which has induced a permanent magnetic field. So it produces undulations in the main magnetic field. So to the right side, you can see that nice picture on the top is kind of undulation in the magnetic field due to this crust. And this is very important for geologists and also mineral exploration and many other aspects. So our model HDGM captures that. We typically use satellite, ship, and airplane data for that, because you need to be closer to the source to measure the data. And then finally, the magnetic field changes with the time. And with short time, in the daily, you can see magnetic field changes. A part of the reason is the electric currents in the upper atmosphere or magnetosphere. A part of the reason is the solar wind. And this is typically measured by a series of observatories. The green dots you see, they are observatories around the world. They measure this time variation. So on this movie, I'll show you a cool example of how do we peel this magnetic field. So what is seen on the right is a magnetic field of the Earth seen from a satellite at low Earth orbiting altitude. And you see the scale on the lower, it's 60,000 to plus or minus 60,000 nanotesla. They are small numbers. So if you peel the main magnetic field, that 95%, you start seeing all these tiny structures. And what you see right now is a magnetosphere. So the currents of the magnetosphere expressed at 430 kilometers. You can see several aspects of this. And then once you remove the magnetosphere, you also have ionosphere. As I mentioned before, we have a dip equator just south of India, which produces this intensification of the currents. And you can see that in the ionosphere, there is a current source which causes large magnetic field just south of India. And this is called equatorial electrojet. And this is from ionosphere. So if you remove, again, ionosphere, if you peel that ionosphere part, there's another component, as I mentioned before, the crustal part. If you go to the surface of the Earth, you have these large rocks, which has magnetized. So that has this distribution of magnetic material, which causes magnetic anomaly. So this is another part. Now, if you remove all this one, you will reach a very interesting, but extremely small. You can see the scale, it's like 2 nanotesla. This is called ocean currents. The ocean is conductive. So when it moves, it's because of its dissolved salt. When it moves through the Earth's atmosphere, it creates a dynamo effect, and which creates small magnetic fields. So scientists have seen magnetic field produced by tsunamis and tides and other things. So this is kind of a general overview of the magnetic field. And now something close to what we do is that we create magnetic field models because magnetic field observations are sparse in space and time, because you cannot be everywhere. Satellites measures only one value at the same time. Observatory stays at the same plane. So a convenient way to represent the geomagnetic field is called by spherical harmonic modeling, which was hundreds of years old. And fundamentally, it says that the negative gradient of a scalar. So Earth's magnetic field B can be expressed as a negative gradient of a scalar potential B. And in this equation, you can think about something like a fast Fourier transform on a sphere, right? That's probably the easiest way to understand spherical harmonic modeling. And these two coefficients, I marked are called Gauss coefficients, named after German scientist Gauss, who invented this type of reduction of magnetic measurements to this Gauss coefficients. And we do the same thing even now, right? We take the data and then we invert for the Gauss coefficients. For example, as we mentioned before, the CrowdMag data. On the left side, you see all the CrowdMag data collected by different citizen scientists around the world using your smartphones. I mean, you yourself can contribute that. We do some initial quality control, and then this is the sparse data set. So when we fit this above model into that, and then you have a model, which is a smooth model of the magnetic field. Once you have a model, then you can predict the magnetic field everywhere. So this is a list. I'm not going to bore you. We say that we develop different kinds of magnetic field models with varying components. As you have seen, different magnetic field have different components in it. Also, we can change the resolution. So we have a world magnetic model. That is our standard model, which is mainly funded by DoD, Department of Defense, and this is used in civilian and military navigation. And also, if you're using a smartphone, you are certainly using World Magnetic Model. We work with Google and Apple because every smartphone has a digital compass and it needs to correct for the magnetic north. And then there are IGRF, some people are using. We contribute to IGRF. This is a scientific research model, but these models are low resolution. Then you can put the crustal component, we can increase the Gauss coefficient degree and order, and then we can have other component as well. But more information at our website. And then what are the uses of the geomagnetic studies and models? So there happens to be many uses. Often question I get is that, why do we need GPS? Why do we need geomagnetic field when there is GPS?